3I Atlas is now officially the third interstellar object ever observed after 1I Oumuamua in 2017 and 2I Borisov in 2019. Unlike Oumuamua's bare, comet-like acceleration without a visible coma, or Borisov's hyperactive but otherwise familiar behavior, Atlas developed a distinct coma and tail, yet behaved in ways that defied expectations. Its trajectory was unmistakably hyperbolic, meaning it is not bound to the sun's gravity and will eventually escape back into interstellar space. But along the way, it has given researchers a rare chance to probe the physics and chemistry of material born around another star. But wait, there's more. Recently, 3I Atlas has shifted orbit against gravity, and gas alone can't explain it. If you're fascinated by discoveries like this, make sure to subscribe so you don't miss future updates. The size of 3I Atlas has been a subject of debate since its discovery. Its nucleus has yet to be directly resolved because of its distance and the surrounding coma of gas and dust. Estimates range from something comparable to a large city block to an object the size of a small mountain, likely spanning several hundred meters across. For context, Oumuamua was estimated at 100 to 400 meters in length, while Borisov was closer to a kilometer. 3I Atlas therefore appears to fall somewhere in between. Its mass and volume are still under refinement, but astronomers agree that it is a significant object. The composition of 3I Atlas is perhaps its most striking feature. Using JWST's Near-Infrared Spectrograph, or NIR-SPEC, astronomers detected that the coma surrounding the nucleus is overwhelmingly dominated by carbon dioxide. Measurements indicate that carbon dioxide is present at concentrations about 8 times higher than water vapor, which runs counter to the pattern observed in most solar system comets, where water ice is typically the dominant volatile near the sun. This may not seem like a big deal, but it's huge. This unusual abundance points to the object forming in an environment far colder than the one in which most of our comets originated, possibly in the distant reaches of another planetary system's Kuiper Belt-like reservoir. In addition to carbon dioxide, JWST also detected smaller amounts of water vapor, carbon monoxide and carbonyl sulfide. The latter is rare but has been detected in some comets, and its presence in 3I Atlas strengthens the idea that interstellar objects carry chemical signatures that can preserve information about their natal disks for billions of years. The heavy dominance of carbon dioxide suggests that the temperature and radiation environment of the birthplace of 3I Atlas was markedly different from our own. In the outer reaches of our solar system, beyond Neptune, water ice can remain stable, but carbon dioxide is not usually retained in such quantities. For 3I Atlas to have this much frozen carbon dioxide, it likely formed in a region colder and more distant from its star than our Kuiper Belt, or perhaps in a protoplanetary disk where carbon dioxide condensation was more efficient. This insight gives astronomers an opportunity to test models of planetesimal formation under varying stellar and chemical conditions, allowing them to compare how different stars and their surrounding dust clouds might create cometary bodies. Another unusual property of 3I Atlas is how early it became active. Activity in comets is typically marked by the formation of a coma and a visible tail, triggered when the sun's heat causes volatile ices to sublimate and release dust and gas. For solar system comets, this process generally begins closer to the orbit of Jupiter or within the asteroid belt. In the case of 3I Atlas, activity was first detected while it was still far beyond Jupiter's orbit, at heliocentric distances where water ice would not normally sublimate efficiently. The early onset of a coma is consistent with carbon dioxide sublimation, since carbon dioxide vaporizes at much lower temperatures than water. This helps explain why a diffuse cloud began forming so far out, but it also highlights the very different chemical behavior of this comet compared to those we are familiar with. Beyond size, composition, and activity, the polarization of light reflected and scattered by 3I Atlas's dust has given researchers another unexpected clue. Polarimetry studies measure how sunlight scatters off dust particles, revealing details about their composition, size distribution, and surface structure. In the case of 3I Atlas, astronomers found unusually deep negative polarization, meaning that the scattered light is polarized in a way not commonly seen in comets of the solar system. Instead, The polarization resembles what has been observed in some trans-Neptunian objects, bodies that orbit beyond Neptune and remain relatively unaltered since the solar system's formation. This similarity raises the possibility that the dust grains in 3I Atlas are more compact, darker, or differently structured than typical cometary dust, hinting at either a different accretion process or a longer preservation in cold radiation-shielded environments. The fact that it matches trans-Neptunian objects also provides a bridge of comparison between our distant icy bodies and those from other star systems. These physical and chemical characteristics make it unlike either of its two predecessors, Oumuamua and Borisov. Oumuamua had no detectable coma and exhibited unexplained acceleration. Borisov behaved more like a classical comet, with water-driven activity and a structure similar to long-period comets from the Oort cloud. 3I Atlas, by contrast, blends traits we have never seen combined before. It is clearly a comet with a visible coma, but the chemistry is unusual. The activity began much farther from the Sun, and the dust properties echo the distant edges of our system rather than the comets we know best. The study of 3I Atlas's physical and chemical properties is ongoing, and its approach to perihelion in late October 2025 will allow astronomers to collect more precise data. Instruments like JWST, the Hubble Space Telescope, and ground-based observatories will continue tracking changes in its composition and activity. Measurements of isotopic ratios in its gases may eventually reveal even more about the stellar nursery it came from, potentially allowing scientists to link its origin to particular types of stars. The rapid advancement of observational technology that has coincided with the arrival of 3I Atlas is also very impressive. Oumuamua passed by too quickly and was discovered too late for detailed spectroscopic studies. Borisov provided some data, but its proximity was less favorable for high-resolution analysis. With 3I Atlas, astronomers had warning months in advance, and telescopes like JWST were well positioned to provide data across multiple wavelengths. So what is so odd about our visitor's orbit? It was clear from the start that 3I Atlas was not bound to the Sun's gravity and would eventually leave the solar system after its brief visit. Yet within weeks of detailed monitoring, reports began circulating that its orbital motion was not conforming precisely to predictions derived from pure gravitational dynamics. Instead, it appeared that 3I Atlas had shifted its orbit in subtle but measurable ways. The basic mechanism behind orbital changes in comets is well known. As comets approach the Sun, volatile ices such as water, carbon monoxide, or carbon dioxide sublimate and escape through jets on the surface. These jets act like tiny thrusters, imparting momentum that can slightly alter the trajectory of the nucleus. In the case of most solar system comets, such non-gravitational accelerations are modest, and their effects can be modeled fairly reliably. For example, Halley's Comet shows measurable shifts in its perihelion timing due to outgassing forces. And NASA's Deep Impact mission in 2005 measured jet-induced changes on Comet Tempel 1 with high precision. The expectation then was that 3I Atlas would display similar non-gravitational behavior, scaled to its volatile content. However, the first orbital refinements from tracking data suggested something more unusual was occurring. Observers reported that the magnitude of the orbital deviation was larger than what standard gas-driven models predicted. The implied change was significant enough to raise doubts about whether normal sublimation could account for it. In comet dynamics, this kind of shift typically demands strong directional jets operating consistently over weeks or months. Yet imaging and spectroscopic observations indicated that the gas emission from 3I Atlas was not especially focused or jet-like, but diffuse. Moreover, while typical comets produce tails that extend away from the Sun due to radiation pressure acting on dust and ionized gas, 3I Atlas displayed diffuse outflow that seemed to project ahead of its direction of travel, rather than trailing behind in a simple anti-solar geometry. Photometric studies showed that the coma extended asymmetrically, almost as if material was being pushed in the leading direction of motion. This is difficult to reconcile with ordinary sublimation processes, which should release gas isotropically, or at least in directions controlled by localized jets on the sunward side. The effect suggested either unusual gas dynamics or an external factor influencing how the material dispersed. Line of explanation being considered is the extraordinary abundance of carbon dioxide in the object's composition. JWST spectroscopy showed that carbon dioxide levels in 3I Atlas were about 8 times higher than water vapor, making carbon dioxide the dominant driver of activity. Since carbon dioxide sublimates at much lower temperatures than water, jets could activate at far greater distances from the Sun, producing non-gravitational forces well before perihelion.